everyone again. Is the session 6, which is on maintenance and repair, which will be chaired by Dr. Alberto Martinetti, and co-chaired will be by Professor Andrew Starr. I think Andrew is here. We can start the session in 5 minutes time or 4 minutes time. The first speaker will be Samir, and followed by it will be by Stefan. Just to the addition of the schedule, we have another presentation from I think 12:25 to 12:45 by Ali Al Yaqub. So that is only the addition of this session. I hope all the speakers of this sessions are there in the room. So I'm handing it over to Alberto. Thank you.
Okay. So we will start in 5 minutes, right?
Start in 5-4 minutes. I'm just putting the links and all these things so people can move around if necessary.
Can you just write down the title of the last presentation that has been added to the session? Because,
yes, I'm just sending you it as like a private message.
Oh, perfect.
Hi, I'm Nitya. Can I try sharing my screen just to check if it is working?
Yeah,
yes,
try it quickly.
For some reason, it's not working. I'll refresh and I'll start over again. I'm sorry.
Okay.
And I think my network is a bit slow. It wouldn't be a problem if I don't share my video.
You have already recorded it?
I'm sorry?
You have already recorded your video, or you are saying that the presentation...
I can share my screen, but with the video, I can just do the presentation with audio. Is that okay?
Okay, that's fine. Yeah. That's fine. Hello, Andrew.
Good morning. Hello, Andrew.
Good morning.
Good morning. How are you?
Very well. Well, fairly well. I pulled my back a bit. But, it comes from sitting in front of a screen for too long.
Yeah.
Hi, Samir.
Hi, Andrew. How are you?
Just saying, I've pulled my back a bit. It comes from sitting over this laptop for too long. But, I shall try to prop myself up a bit and just have to stop complaining. Nobody's listening.
Alberto, I think we can start. Andrew was saying something.
I was just going to ask Samir, how are things in Japan?
They're all right. It's so the pandemic's kind of settled down over here quite a bit, and things are looking quite bleak in the UK from all the lockdown and all that things that I've been watching in the news. So yeah, hopefully everything is going to go smoothly in the UK.
Yeah. Well, I just wanted to mention to you that the university is open. The cases around Cranfield and also where I live in Hertfordshire are extremely low. But I wouldn't plan a trip to Manchester or Sheffield right now.
Okay, sure.
Central London's building up as well, so that's the real reason it's happened. The big cities are building up.
Alberto and Andrew, we can start the session.
Yeah, okay, so 10:45, so we've got to
Yes.
say hello to our audience. So our first presentation, I'm glad to see that our speaker is here, Samir Khan. Welcome, Samir. If you'd like to share your screen, over to you.
So can everybody see the screen?
Yes, yes, we can see you.
Yeah.
Okay, super. So I'm going to start the presentation. Hello, everybody. My name is Samir. I work at the University of Tokyo, and the paper that I'm going to present today is to do with some work that I did with John on the No Fault Found project a few years ago. Actually, that it was about 6 years ago. And this was an MSc project, and we reasonably started off quite well, but unfortunately the student wasn't able to publish a paper on it at that time. So we got together eventually and we decided to write a paper, and we thought that the TestConf 2020 would be a good idea to have it published and talk about it. Okay. So the idea behind the paper was to develop an agent-based model for a problem called the no-fault found problem. And what it is, I'm going to talk about it in the presentation. That's the agenda for today. I'm going to talk about a little bit about the problem and how does agent-based modeling actually start off in that context. I think agent-based modeling had a lot of potential when it came to modeling the no-fault found problem. And you're going to see it in the presentation as we move on. So for those of you who are not aware of what no-fault found actually is, no-fault found is basically any problem, any critical problem within any system. It could be an aircraft, it could be a railway system. And the idea behind it is that whenever there is a fault, you either cannot isolate the fault or you cannot diagnose the root cause of the problem. One way to look at it is when you have an aircraft flying in air. In the diagram on the left, you have a civil aviation aircraft where the pilot sees a red light. He reports that I saw a red light, which probably indicates a fault. So when the aircraft lands, the engineer comes and he tries to diagnose what the fault was and where the fault was. If the engineer is able to find the fault, he will replace the component in the aircraft and put that aircraft back in air, because this aircraft is no good going under maintenance in the hangar. It's only good when it's generating revenue and when it's flying. This is the case for civil aviation. Military is slightly different. But in the context of civil aviation, the engineer would want the aircraft to be flying in air. That's why availability is very important. But what happens if the engineer on the first line maintenance cannot diagnose that fault? Well, it puts that into another loop where you would send that component, you will remove that component and send it to second line maintenance, which will presumably have a little bit better equipment to diagnose what the fault is and what's wrong with the component. Well, they will try and fix it. If they can find what's wrong with the component, then they will obviously put that component, they'll repair it and put it back into the inventory. Of course, all these diagrams and all these arrows, they're very simplified processes for the purpose of this presentation. Of course, there's a lot of complicated stuff that goes around. So, okay, let's get back to diagnosing the fault from second line maintenance. Let's assume that the engineer or the technician is not able to find anything wrong with the system. Well, what do you do then? We've got a no fault found problem. Now, this is quite it costs a lot of money to organizations, because you're essentially wasting maintenance activities on looking for a fault which may or may not even exist. Maybe and it raises a lot of questions about maybe the pilot made an error when he reported a fault. Maybe the maintenance equipment, the test equipment, is not adequate enough to detect a fault, and subsequent tests So there's a lot of ambiguity associated with diagnosing that there was a fault or whether there was no fault at all when we started looking at this problem. This issue gets compounded by the fact that all these boxes that you're looking at, these dotted lines, these could be represented by different organizations. Now, as the number of organizations keep increasing, so the operator, for example, perhaps the operator reports that there was a fault, then the OEM might be the ones who are looking after the maintenance regime for that particular operator. There are going to be communication gaps. There are going to be information which might not be transferred. There's so many other issues which can contribute to what no fault found is. The image on the right-hand side basically explains the mapping that we did during the no fault found project. And you can get a feel of how broad the problems can be brought about because of no fault found. You know, there can be problems with training in management where people might not even recognize that there is a problem. And a lot of this no fault found issues, a lot of this depends on the culture within the organization as well. Something that I have personally been working a lot on is the use of intermittency. Well, intermittent faults is basically can be classified as a no fault found problem. Of course, there are different types of intermittent faults. Some of them grow, which is a big concern. Some of them don't grow, and they do not alter they do not affect the availability of the system. So those type of intermittent faults are not the ones that I'm going to be dealing with, or we were dealing with. We were dealing with faults that actually resulted in a no fault found problem. I think that's pretty much what I wanted to discuss from this slide. I'll go on to the next one. Okay, so after understanding what no fault found actually is and how it kind of grows, we were in the process of trying to model it at different levels, and we were having a number of discussions with several engineers, and there were options like modeling no fault found processes using Petri nets, and agent-based modeling obviously came up as well. And the idea was that you will be able to model the environment in which the no fault found problem or the phenomena exists. And what we want to do is basically try and model all the whole process, the whole maintenance process, and try and understand why this phenomena actually occurs within the supply chain. And you know, the overall motivation being trying to understand how we can minimize and manage these issues in the supply chain. So the image that you are looking on the screen is essentially describing the environment within an organization where the fault is being experienced. You know, this is a simple Markov chain process where you will need to define rules. So the first rule would be you have a working component. You know, it could be a line replaceable unit, and which is operational. The second rule would be that you might have intermittency in your components. So it's going to go from an operating state to a non-operating state. And of course, this switching between operating and non-operating, if it's an intermittent fault, you know, there might be very little time to failure. And then time to repair. You might not even need to you might not even need to deploy an engineer to repair the fault, because intermittent faults, they come and go. They're quite elusive. So that could be your second rule, where you will essentially express that I have intermittency in my system. But you know, you can introduce a third rule, which kind of makes it a bit more interesting, is when you have multiple units that can talk to each other, and some of these units are dependent on each other. Making it a little bit more interesting, or extending it from there, you can change the environments as well. So you're working in the operating environment where the operator is working on an aircraft. You can have another environment where you're going to have the maintenance organization, which is trying to deal with this. And then you can have another environment where the supplier is trying to deal with these problems. So there's a lot you can do with agent-based modeling, and the idea when we were sitting down and discussing these ideas, we thought that introducing some simple rules to add to the behavior of these agents, whatever agent we choose, in our case, the components which are experiencing NFF, we might be able to map the whole process and identify some of the root causes of the problem, and even improve our understanding about the phenomena in general. Okay, I think that's all I wanted to discuss on this slide. So in this case, it's a bit more, so it's got a lot more elements to it, where you've got multiple units. And I think the idea that we initially proposed was you can have different kind of behaviors. So you can have different types of technicians. Some of these technicians will have different levels of experience. Some of these technicians might have better equipment. Some of these technicians might be working during the day, or during a certain number of working hours. So there's a lot of variability that we were hoping that we would add to create a much more realistic model. Okay, so in the next slide. So to start off, some of our requirements within the industry, of course, you need to have the ability to, because you're working with so many different components, you needed the ability to dynamically interact and change a lot of these components during the simulation. And at the same time, we wanted to monitor the different types of scenarios, the NFF scenarios that can take place. And we're going to talk about some of them in the next few slides. But the following bullets, all of them, they were kind of the requirements that we wanted to achieve within the MSc project. The student wasn't able to achieve much of this, but to be fair to the student, NFF is a very complicated problem. It's even complicated for us when we try and analyze some of these situations. But some of the stuff that we did highlight was quite interesting, because you can have different types of components and the number of maintainers that you can change and vary. It still is an interesting project, and given the time and opportunity, I think I'm going to pursue further research on this topic. Something which was very interesting that I was actively working on was modeling the culture of organizations using agent-based models. And there were some interesting papers which have actually implemented this type of behavior on how different cultures in organization influences their results of their decision-making process. So the first job that the student had to do was go and do some data collection. And a lot of this work has been discussed in the paper, and a lot of this work has been mentioned in terms of like the survey results have been published as well. We, at that time, 2014, 2015, we were organizing a symposium on NFF, and that gave the student a good opportunity to go and talk to some of the experts. So he was able to go and talk to some people to find out more about the problem, the NFF problem, and the whole idea was to try and map the problem in some way. I'm going to skip some slides
Sorry,
in the interest of time, but just to give you a description of what the actual mapping process resulted in. So whenever you have, if you're looking at the top image, you're looking at when NFF takes place. This image basically highlights the process and the decision-making process at the operator's level. So when the operator faces an NFF problem, they essentially have three options. They can either return the unit to the system provider, which is the OEM. They try and solve the problem by themselves, which is going to affect their availability if they cannot find the problem and also incur costs. Or they can just ignore the problem, which unfortunately was the case in many operating organizations. If they do decide to send the unit back to the supplier, you go into the second diagram, which has a different set of processes, but essentially the second system provider, the NFF2, has four options that they can choose from. they can either send their product to their supplier from where they procured it from. They can send it back to the operator by telling them, well, we cannot find anything wrong with the component, so it's your problem. They can do extra tests, which obviously the cost of these tests will be absorbed by the operator. They can either discard the unit. So if it's a repeat offender, if this particular unit has been in the cycle for long, you're going to discard it eventually. This researching this basically reveals that NFF actually can be a very lucrative business, because you can essentially keep charging the operator for a fault which does not exist. Okay, so if the supplier, if the system provider wants to send the unit for further testing, they can send it to their supplier.
Samir, sorry.
And they will.
You have 1 minute left.
Oh, okay. So they will send it to their supplier, and they will try and deal with those problems from that point of view. I think the overall, in the end, the student was able to come up with a framework to implement. And however, he didn't get an opportunity to do many simulations of the result. But I think from a project's point of view, we were able to map the whole NFF process. And in the future, we're looking forward to model the behavior, trying to understand how the problem originates and how it propagates through the whole supply chain. I think that's about it. I'm going to end, and I'll wait for some questions. Thank you.
Thank you, Samir, and thanks, Alberto, for doing the timing there.
No problem.
So I have a question to kick things off. You've
Sure.
spoken a lot about the nature of NFF and its taxonomy. How does it affect some of the overall indicators like reliability or availability?
Okay, so I think that's a good question, Andrew. And the problem that we've had is that if you consider NFF as a problem, it's going to affect reliability, because you're going to factor in NFF in your metrics when you calculate your metrics. But most of these organizations that we were working with, they didn't really recognize the problem, or rather, they didn't really recognize NFF as their problem. So they did not have any metrics for NFF in their calculations. It is a very subjective issue, and you ask somebody else, they're going to give you a completely different answer. But I think it's quite difficult for organizations to evaluate accurate reliability metrics for NFF still today.
Okay, thank you very much. Well, looking at the time, we're at 11:04 on my computer clock. So I suggest we get Stefan set up in a moment. But Samir, if we can thank you most warmly for your presentation, and we give you a virtual round of applause.
Thank you.
Thank you very much, Samir.
Thank you.
Okay, Samir, if you could unshare your screen and close your camera, then we'll allow Stefan to get ready. Good morning, Stefan. Welcome.
Good morning. Nice to be in the same room virtually. Unfortunate
It's
this
fabulous,
year,
isn't it?
That's
what a crazy
how the world
experience.
has to work now. Okay, I will share my screen so we
Yep.
don't lose any time.
Thank you very much.
Okay.
So Stefan's session is going to tell us about voice-enabled digital assistants for predictive maintenance and manufacturing. Stefan, the floor is yours. You've got 15 minutes. It's just disappeared there.
Yeah, I think you have refreshed the browser, probably. Seems, yes.
PowerPoint, now it works.
Here it is.
Yep.
Okay, this is the
Over
camera.
to you
Okay.
then.
Okay. So I will not lose any time further. You can understand me. You can see the screen, I guess. The presentation.
Yes, we can.
Okay, good. So, yeah, my name is Stefan Welsand. I work for the Research Institute for Production Logistics in Bremen in Germany. And I'm going to present you a concept of a voice-enabled digital assistant for predictive maintenance in manufacturing. We worked on this topic together with the TU Delft, and I will present you first an introduction of the background of this this activity. I will say a little bit about what a digital intelligent assistant is, its general advantages and the challenges that we identified so far. Then I will say something about the goal and scope of the paper, the results, the discussion, and then conclusion and outlook. Okay, so the background or the domain that we're targeting with this work here is maintenance in manufacturing, and that's typically a heterogeneous field. There are activities close to the shop floor, executive activities, failure diagnosis on machines and something similar, and planning activities. So, for instance, maintenance program design and so on. Something that is crucial for these activities is the access to information about very different things, ranging from people to items in the field, and some more abstract pieces of information also. And you can imagine if you have to access this information, then it's somehow interrupting work that you are actually doing. So you might need to interrupt what you're doing. There can be short interruptions to access a local interface, typically a graphical interface, and there can be longer interruptions, especially when you have to move between facilities to get to a place where you can access certain information. And our idea was that we could use maybe one of these assistants that you know from the consumer domain, Alexa, Siri, and Google Assistant, or other similar assistants in this field here. And that is setting the stage for our work. We know that there are companies out in the field that do this already, but it's very difficult to get information about what they do and what their assistants can do in this field, because it's not publicly available or they are very sparse in providing it. Okay, just quickly, what is a digital intelligent assistant? So first of all, it's very similar to what Alexa or Siri or any of the other consumer-oriented assistants is. It's a type of artificial intelligence, something that appears to be intelligent because it can answer questions, it can do things for us when we ask for it. The capabilities of this this kind of an assistant of an artificial intelligence depends on the skills that these assistants have, and skills are very similar to the apps that you have on your smartphone, for instance. So each one provides a piece of functionality, and oftentimes the skills are directly communicating and interacting with other computer systems, not part of your assistant as such. They can be asset monitoring systems that run somewhere in the company, for instance, or programs to do data analytics. Then we identified 3 areas where a digital assistant can provide advantages. None of these is exclusive for a digital assistant, but I would go through them here and then make my point in the end. So the connectivity means that an assistant is typically connected to a variety of information systems inside an organization. That means that workers that have a digital assistant can use it in a sense of a personal library. You can ask information about items, persons, processes, systems, and so on. The second aspect is proactivity. So the assistant can manage problems for you before they hurt you, before they become dangerous to you, and that can be done in a simpler way by rule execution, or in a more complex way with decision-making models that you trained maybe with machine learning or similar kind of techniques. And then the last aspect, which is very visible, especially in the consumer field, is the natural language communication. So with an Alexa or Siri, you communicate via voice typically. You can also communicate via text in a similar way as a chat, but typically It's voice, and that means that the assistant is able to hear you, it's able to talk to you, or read and write also. And the aspect of voice brings some unique advantages for using an assistant, because you can use it without your hands. That can be very beneficial for certain tasks, not all of them, of course, but for certain ones. And using voice is typically faster than writing, especially when you are not skilled in writing very fast. Then voice is faster than writing. So what is special now is that a digital assistant is collapsing all these three advantages in one solution. While other software solutions typically cover one or two of these aspects, but not all of them. And that makes the assistant an innovative piece of technology and also an interesting research field in our view. And through the course of our research, we already identified a couple of challenges, interdisciplinary challenges. So things that require further research and are also very difficult to solve in some way. So first of all, it's not so clear yet what kind of benefits these, especially voice-enabled assistants, can bring for industrial tasks. Then we have the problem of personal data protection. Simply asking, do you trust Amazon, for instance, that they take care of your company and your employer's data in some way? The answer to this, we found out, is typically no. So you need to look for other solutions here rather than what Amazon or Google offer. Then you don't know what happens to the knowledge that you communicate via an assistant, especially if it's hosted on one of the large IT companies' premises. It's not clear what it means for data security risks. There can be eavesdropping of conversations, injecting false information. The robustness of these solutions is also not very good under industrial conditions. You have noise typically, you have time pressure at work, and that means you cannot just have long, lengthy conversations with an assistant to hit the point where you want to execute a certain function or something like that. The acceptance among employees is critical for the assistant's success, but also it's very difficult to convince people to use it for fears of being replaced sometimes. There's accountability, so especially when an assistant gives you an advice that is leading to some severe problems like injuries, then the question will come up, who's accountable for that? And in general, there's a lack of experience right now how humans and machines converse with each other directly. So how would you talk to a process? How would you talk to a machine? The scope and the goal of this paper is that we say it's necessary to have hands-on experience with these technologies, not theoretical thoughts. There are a lot of papers also about the theory, how people could work with an assistant. But what we say is that you need to have the practical experience to understand the design problems that you face with this kind of an assistant application. And also you need to understand what the technology limitations are. In particular, now you find this out pretty fast when you try to challenge your consumer devices like Alexa or Siri, for instance, and then you find out that there's oftentimes the case where they don't understand something. So our research focus here is on figuring out how to design digital intelligent assistant, especially for maintenance and manufacturing, and how we can create time-efficient dialogue structures. So not simply replicating dialogues that mimic a little bit what you do with the graphical interface, like going through menus and these kind of things. It's a different way of designing access to information, and that was the scope of, or is the scope of our research. And in order to make some progress here, we said that we need to first identify, of course, who would be the potential users in the field of maintenance and manufacturing, and then what are their requirements. And of course, then we come to the point where we need to see what kind of functions should this kind of an assistant have, and how do we organize these functions. And that's the concept that I'm going to show you in a moment, the result of this paper here. First, we identified three main users that would benefit from an assistant. The first one is the maintenance coordinator, the person that coordinates and assigns resources to perform maintenance tasks, and that also approves, for instance, maintenance reports. Oftentimes they use kind of indicators for this. Was a task already accomplished, or what were the downtimes of a machine? The second one is the maintenance technician, so the person that goes to the field when there has to be some kind of maintenance activity, inspection, or even repair, then and the reporting of the task, the results, and the overall context of what was done. That is in the field of the technician. And in some cases, operators, machine operators, sorry, they have the they are very they can be very useful, beneficial to consult or involve here as well, because they notice abnormal machine behavior first, typically because they are the ones that work with the machines in their shifts. And sometimes they're also entitled to perform simple maintenance routines. So they do some small maintenance tasks by themselves sometimes and could use support in those tasks. Then after some further investigation of use cases and the requirements, we came up with a functional diagram that you see here on this slide. This is, in our view, a starting point for discussion. So it's not that we say this is the only one that is possible. It's a meaningful one that we consider as achievable also with the technologies today. And it's structured into three areas. The basic functions in this diagram, they are necessary to enable conversations on a very basic level and allow for very basic conversation patterns. On the right side, you see a chat history that we have with our assistant. So that simply shows that you have different stages of a conversation. You say hello when you start engaging the assistant, and you say thanks to close the conversation, for instance. And then there are some very basic functions that you use in many kinds of conversations. The second one is the utility functions, or other utility functions, and these ones are provide assistance for small but frequent problems that come up. That can be setting an alarm, checking a to-do list, using timers, stopwatch, and those kind of things. These functionality is oftentimes, it comes with the consumer assistance on the market. So they already can handle these kind of things. So you don't oftentimes have to develop your own solution for that if you use one of the existing solutions on the market. And then we come to the point where it's much more specific for this domain, the maintenance functions. These really are tailored for maintenance, and we identified 5 areas for this kind of functions. And a very simple one you see on the right side, where we interact with the assistant, providing an ID of a workstation. We ask what's the status of this workstation, and we connect with the machine, and we receive the status of the workstation, that there's, in this case, a problem, and then you can continue the conversation asking, why is there a problem? In the next stage, you could ask, describe the problem in a more detailed way by explaining the failures, the failure codes to me. And of course, you want also to navigate through the various problems that can come up in a failure. So that's why you see here there are 2 more components available that in this case have failures. Okay, the discussion covers some aspects that we identified. First of all, technology-wise, there's the big bottleneck regarding the speech-to-text mechanism. That's the mechanism that turns the audio into a text that the assistant uses further. Oftentimes, the problem here can be pinpointed that open solutions like Mozilla Deep Speech, they are not so accurate, and the closed ones, they're not so transparent. So there's a trade-off here that you need to consider
1 minute left.
that decides what you can do or what you can implement. They're useful practices. You need to involve workers despite language problems, despite knowledge problems, because those are the ones that really use your assistant. And if you are not having them on board, then you're not going to make much progress. The conclusion here is that we see some technical and non-technical challenges. Interoperability of the business information systems is a big problem, and so is also education programs for workers and accountability of assistants. And the list becomes longer if you consider that especially the European Union pushes this AI ethics topic significantly, and there will be a lot of things to consider that are not technically or not technical. Sorry, and solving them goes way beyond what research can do. There's political concept that is needed to deal with certain problems, and also acceptance among the industry, of course, for these kind of technologies. Thank you. That is my presentation. I would like to make you aware of two projects that we have in this field here. One is an EIT project, EIT manufacturing project called Diamond, that's focused on maintenance particularly, and is also the reason for this paper here. And the other one recently started is called Koala, and there we are developing a factory assistant in the course of the next 3 years. Thank you.
Vielen Dank, Stefan. So we have a question from Ali, who compliments you on the work. What libraries are you using for the chatbot?
Okay, so the general idea was that we reuse things that exist, open source projects. In this case, we use Mycroft, which is an open source assistant framework. They also come with their own hardware, and they claim to be privacy focused. And that's a big positive thing that we want to bring here also in the manufacturing domain. So Mycroft is the main technology that we use here. And for the speech to text, we use the Google, unfortunately, but we are heading forward to see if we can work with Mozilla Deep Speech also, as that becomes better, and it's an open source activity. So that is hopefully solving some of the problems of mistrust against the big IT companies.
Thank you. And you mentioned earlier working across Europe and its ethics, but clearly Europe uses many different languages. There are after January, there'll be 27 members with far in excess of 27 languages, I suspect. So what do you think are the challenges of dealing with different languages and indeed accents within a single language?
So what I think about this is that this is a problem that someone else is working on. Frankly speaking, it sounds a bit blunt, but there are very good solutions out in the field already, especially for the languages spoken by larger parts of the population, not dialects in particular. That's a bit tricky, and you need a lot of training data to cover this as well. But there are good commercial solutions out in the field, I would say. But in the open source domain, it's not so good yet.
Sorry, Andrew, I just was asking the same question you did. I just posted on the Q&A. The multi-language question, it was when I was going to ask. And let's go further. How you see this being developed outside Europe, the multiple language problem? Is it centered in Europe, the problem, or is it global?
I mean, the problem is global. If you see how people, especially in the Common Voice project, where they collect training data for language models, you see there is a big inflow of dialects, also of smaller or languages where you don't even know they exist. So it's a global problem, but the solution is also powered by people all over the world. And that's good, actually, because the only reason why Google or Amazon or Apple are good in this field right now is that they silently take the data from their customers, and they do what the open source community is now doing in a more transparent way. They do it hiddenly. That's the only reason why they are so good at it right now with their own commercial solutions. So the magnitude of this problem is global, and I would be very happy if we end up at some day that we have a solution that works everywhere on the planet.
Okay.
But it's not a solution I provide.
Mindful of
Thank
the time, we are biting into the next session. Thank you ever so much, Stefan. That was a very interesting presentation. Virtual applause.
Thank you very much.
Thank you.
So now our next speaker is Janardan, and if we could invite him forward, please. Welcome. And Janardan's presentation is about challenges for on-site automated ultrasonic phased array inspection on aircraft structures. So Janardan, the floor is yours.
Shall I share the screen?
Share your screen, please.
Please do that.
Yeah.
We will close out. I'll just leave the mic on because everybody asks, can you hear me?
I hope everyone hears me.
We hear you and we see your screen.
Yeah, thank you very much. Hello, everyone. I'm Janardan Padiyar. I'll be presenting this topic entitled Challenges for On-Site Automated Ultrasonic Phased Array Inspection of Composite Aircraft. And these are my co-authors. This work has been carried out at Center for Autonomous and Cyber Physical System at Cranfield University. This is the agenda for today. I'll be briefly talking about NDT of aircraft structure, and then I'll be dealing with the challenges and the development of a phased array module, its technical development, and some brief inspection trials, and integration of the phased array module with the robot, and some conclusions. So coming to the maintenance of aircraft structures, NDT is one of the basic jobs of maintenance of aircraft structure. Generally, NDT is performed using manual inspection, and depending upon the type of aircrafts, about 35% of all inspection tasks in composite aircrafts are by ultrasonic NDT. Ultrasonic NDT for composites use two types of transducers. One is single element ultrasonic transducers, where there is only one element involved, and multi-element transducer, usually called as phased array transducer. Now, both these transducers are used for manual inspection. However, manual aircraft NDT inspection are quite repetitive and slow, specifically for large surfaces. Cost of scheduled maintenance of aircraft is quite high, and also when the aircraft is on ground. Sorry for that. Aircraft is on ground for inspection. It will be away from service for 3 to 6 weeks. For example, say for Airbus A320 series aircraft, C-check maintenance and D-check maintenance involves about 150K to 350K per aircraft. D-checks are carried out once every 72 months. However, it's found that the recent composite aircrafts, which have more, particularly Boeing 787 and Airbus A350, have less inspection schedules, but they still have inspections during third year, 6th year, and 9th year, and 12th year. The C checks are very simple NDT inspections. D checks inspections are where the entire aircraft is ripped apart and again reassembled before inspection. Hence, fully automated or autonomous NDT solution is a requirement. However, this is still are at a research stage. Coming to the why NDT is required for specifically for composite structure is due to a kind of damages which occur commonly called as impact damages. New aircrafts models such as Airbus 350 and Boeing 78 series have greater than 50% composite material by weight. These fuselage skins and wing skins are highly susceptible to impact damages during service. Impact damages can be classified as visible to the inspector or barely visible. These barely visible impact damages is very difficult to find, but there is a large size of damage below the structure. Hence, I think my mouse is moving. Okay, so it is skipping to the next slide. So on the left side, you can see a figure. This is from the Airbus. It says that during the life of the aircraft, these are the locations of the impact damages that occur for the aircrafts. So these impact damages will result in may result in repair or repair during scheduled inspection, depending upon the size of the aircraft. Hence, a regular inspection is required for maintaining the continued airworthiness of aircraft. So coming back to the transducer, phased array transducer is similar to an ultrasonic transducer, wherein instead of one element, you have multiple element transducer. This transducer is specifically preferred currently due to its speed of inspection and also due to the image which it provides for sizing the damage. On the left side, you can see a schematic of how the transducer sends the beam, ultrasonic beam, into the material, and it is recaptured, and that beam is traversed electronically from one end of the transducer to the other. So there is no need of scanning in one direction, whereas there is a mechanical scanning required in the other direction. Hence, this kind of scanning is much faster. The work which I am presenting here is a part of a project, EU project called Compinova. This project is having 5 partners. 4 are from universities and 1 is an SME partner. The main aim of this project is to automate NDT inspection and automate the repair of the damage, and also use a robotic platform for inspection. In this project, we at Cranfield are responsible for developing a phased array ultrasonic module which can be mounted on a robot, which can travel and that it can traverse over the aircraft and inspect the aircraft. Moving on, the objective of this work which I am presenting here, it is to develop and integrate a phased array ultrasonic module for inspection of thin-walled aircraft composite structures based on meeting the constraints set by the Vortex robot on the payload of the phased array ultrasonic module, and also very low water couplant usage as the main constraint. So we had to develop this phased array ultrasonic module. So however, there are no such modules available commercially or or at a research stage. So we had to look at other sectors of industries to find out how they are doing inspection. So if you look at oil and gas NDT inspection, there they use a kind of robot which is having magnetic wheels and which attaches to the surface of tanks or pipes and moves over the surface. So essentially these are magnetic based, adhesion based crawlers on which different NDT modules can be mounted to inspect the structure. So based on this background, we set out to develop a phased array ultrasonic module for inspection of aircrafts. So our solution consists of a soft elastomer wedge, a new couplant delivery mechanism, and a communication controller to control the phased array hardware by the robot, and selection of other equipments which are required for the development of phased array module. Next, moving on to the phased array module development, the PA transducer or the phased array transducer, the requirements for inspection of thin composite structures are quite different from general phased array inspection for metals. Generally, we need to use a higher frequency transducer so that we can get a higher image resolution, and some near surface resolution and dead zone is prevented. But there is still a constraint that we need to use a lower weight transducer and a smaller array length due to the constraint set by the Vortex robot partners. So we looked at different transducers and used a beam model to understand the beam characteristics of types of transducer, and then we selected on a 10 megahertz 64 element as a PA transducer. However, we also looked at commercial solutions for aircraft inspection. Currently, a it's called as a wheel probe and a thin membrane wedge. These are the two state-of-art wedges that are available for manual composite NDT inspection. However, when we evaluated these two, we found that the wheel probe is quite bulky and it requires a considerable force to get good signals. And also, when we tried to use a thin membrane wedge, we saw that a thin film of water has to be maintained, else it will result in false negatives. So both of these current state-of-art wedges were not suitable for automated inspection for our particular use. So hence we went to design a new wedge. This wedge is a soft elastomer contact wedge. It is made of hydrophilic elastomer material. It is having a very low attenuation, and since it's made of elastomer material, it's quite light, and it can be used for any kind of wedges. So we designed this wedge thickness, that is the delay line thickness, and the material from a local partner. So this transducer has to be mounted on a fixture. The need of fixture is to inspect the cylindrical surface or near to cylindrical surface of fuselage of aircraft. This fixture is needed since the transducer has to be maintained normal to the surface, and there should be a constant contact during the scanning process. So based on this requirement, a particular spring-loaded positioning fixture was selected. Now coming to the water couplant, water as a couplant is used with ultrasonic transducer for coupling the ultrasound from the transducer to the surface. If there is no water, then there is no transmission of ultrasound into the surface, and hence it will lead to false positives. So in general, now they use either free flowing water or a spray of water. Free flowing water is not possible because of the robot constraints. And when we saw the spray of water, we found that it is not suitable for automated inspection.
You want 1 minute left.
Yeah. So we went for, instead of spray, a mist-based couplant delivery. And these are the initial inspection trials. We found that the performance of the wedge meets the requirement, and also it is having a equivalent it meets the requirement, and also it is similar to the commercial solution. So then we integrated the PA module onto the Vortex robot. On the left side, you can see the PA module attached to the robot, and then you have a mist delivery with a conical shroud to prevent the mist falling onto the motor, onto the electric motor of the robot. A communication controller was also developed, which using this, the robot can control data acquisition and actuate the pump to switch on the mist delivery during inspection. So the automated, then we move on to a realistic scenario, a large stiffened composite structure. On the left side, you can see, on the left diagram, you can see the stiffened composite panel. On the right side, you can see the two robots. One of the robot is having a Vortex, having a phased array module, and another robot is having an infrared module. Both these modules are used for inspection of impact damages on this structure. So the inspection plan is in this way. Initially, the infrared thermography module, which is mounted on the robot, moves across the surface and does inspection to find the location of the damage, and then the phased array module is mounted on the robot, and then it moves to that particular location to find. So these are the results of the damage. We see that damage can be easily identified, except at the web region. So this PM, the developed PA module is also.
We need to ask you to go
used
to a
inspect
conclusion.
a repaired patch, and we have found it successful. I'll just conclude. To conclude, these are the key conclusions. The developed elastomer wedge was found suitable for both automated and autonomous scanning. Mist couplant delivery ensures a uniform couplant distribution with minimum water. And the Vortex robot scanning with PA module is found to give very repeatable C scans on flat surface. Due to the pandemic situation, we still have to trial on the aircraft grade fuselage panel. There is still some scope left where we can come up to an industrialized solution using umbilical cord free PA module and Vortex robot.
Okay, thank you very much. Really,
thanks, Janardan. I think we've run out of time there, so I did have a question, but we will have to say thank you very much for your presentation, and virtual applause, and we'll move on to the next session. So can I invite Udemy up to the stage? Hi, Udemy. Now then, Udemy is going to tell us about learning-based diagnosis of multiple faults in bearings. So Udemy, if you'd like to share your screen, I think I could ask Janardan to unshare his screen and camera. Thank you very much. Then, Udemy, the floor is yours. I'll just leave the mic on to confirm. Yes, we can see your slides.
Good morning, everyone. I hope I'm being heard. Can you hear me clearly?
Yes, we can.
Okay. My name is Udemy Yang, and I'll be taking you through my paper, which is on learning-based diagnosis of multiple faults in bearings. Paper was written with Dr. Ivan Petroni and Professor Jennings. Yeah. My presentation will cover the background methodology, data set that I used, and key discussions and conclusions. Rotating bearings are actually critical components that are found in most machines, which include gas turbine and wind turbines. These bearings actually have various parts, and these parts include the inner race, the outer race, the ball, and also the cage. Due to the difficult environment in which bearings operate in, and sometimes due to the manufacturing procedure, they are actually prone to failure. And researches and surveys have actually shown that about 48% machine failures can be attributed to bearings. And so it becomes really important for the diagnosis of bearings to be carried out. So typically, when the bearing have a fault, is actually in the spectrum is actually a presence of an increased amplitude of the characteristic frequency. And depending on the fault that is present, if it is the outer race fault, the band pass frequency of the outer race will be magnified. If it is the inner race fault, the band pass frequency will have an increased magnitude. And if it's also the ball fault, ball spin frequency also have an increased magnitude. However, there's actually a part known as the multiple faults, and multiple faults actually involve the presence of two or more faults in one or two bearings. And these multiple faults are quite challenging to diagnose. The reasons include because of overlapping frequencies, which could be present in the bearing fault signal. Another reason has to do with the coupling frequency component, and also a particular fault, assuming the multiple faults in the multiple fault signal, assuming there are two particular faults, say inner race and the outer race faults being present. One of the faults may be weak, and while the other one is strong. So you may have that one fault masking the other fault. So this makes the multiple faults of the bearing to be quite challenging. And a particular case can be found in the helicopter crash that involve a particular helicopter in 2016, in which 17 persons perished on board the aircraft. So to carry out this particular research, a literature review was actually conducted, in which we saw that some signal processing techniques were actually developed and used for fault diagnosis. We'll also so that machine learning techniques and in combination with signal processing techniques were also used for the fault diagnosis. And recently, deep learning approaches have been used for the diagnosis. Well, from the literature, looking at the three key methods that have actually been used for the diagnosis, we actually saw that these approaches actually have inherent weakness. For the signal processing techniques, we actually observed that most signal processing techniques were actually improved for single fault diagnosis, and those that were actually adapted for the multiple fault diagnosis would only work in a particular situation. Say, for instance, a combination of signal processing technique being used for the bearing and the shaft diagnosis may not be suitable for using the gear and bearing diagnosis. That's in a case where I'm having multiple faults of the bearing and the gear being present. Also, the machine learning approach being combined with a signal processing technique, we observed that this particular approach actually required the use of a manual feature extraction method, and that a design of a feature extractor may, for one problem, may not actually be suitable for another problem. And also this method involves the problem of having detail loss. Like I said earlier, that the deep learning approaches have now been used for rotating machine and multiple fault diagnosis in bearing. So key among the deep learning approaches is the CNN, and we also observed that the CNN was actually being focused for a single space feature being used for the diagnosis of bearings. Hence, it became an imperative that there should be a creation of a flexible approach that utilizes more than one feature space for diagnosing multiple faults in bearing. And in doing that, we actually came up with a methodology that involved having the sensors that we use for the acquisition of the data to get the multiple faults signals. And then we had a technique, a short-time Fourier transform, and being used for one of the CNN, the deep learning approach, and also the bispectrum analysis being used for another deep learning approach. The results from this approaches were now we used an ensemble learning, and also before we now had the final diagnostic result, and that formed our method that we use for this diagnosis. So the deep learning, the ensemble learning is actually a machine learning approach in which we try to combine different models to actually solve a particular problem. And in this case, having different deep learning models, the output from these deep learning models can actually be combined to have the final result. The technique that we used, the signal processing techniques, included the short-time Fourier transform. And in the short-time Fourier transform, basically what happened is that the multiple fault signal is actually broken into various segments, and then FFT is performed on each of those segments. Also, we also use the bispectrum analysis, which is a kind of higher order spectral analysis method, and it is actually effective in non-linear detecting non-linear coupling in frequency components. So the another key component that we had in our approach actually involve the CNN, and the CNN actually is made up of different layers, and the key among these layers include the convolutional layer, the pooling layer, and the subsampling layer. So to the data sets that we use for this study, we used the Case Western University bearing data set. The Case Western University bearing data set actually involved two bearings, one on the drive end and also the other on the fan end of the bearing. And the bearing signals were actually sampled at 12 kilohertz. The different faults that were present actually had different severity, with the highest being 0.5334 millimeters, and different loading conditions were also present, ranging from 0 horsepower to 3 horsepower, and different rotating speed of shafts were also present. So for this particular data set, we had that the inner race fault had a particular characteristic frequency, which is obtained by multiplying 5.4152 by the rotating speed, and the same for the outer race, and also for the ball faults. So we then move further to have to process the data that we have. We started by making the short-time Fourier analysis, and having the spectrogram from these images, and also we did the bispectrum analysis, and also having images from these from the multiple fault signal. The size of the images that we actually got from the multiple fault signals were 224 by 224 pixel, and in actually pre-processing this, we considered key things, and readable, and having a good resolution, and that also the for we used 1024 data points in creating each of the image. In choosing this, we tried to ensure that it wasn't computationally expensive. For the bispectrum, we had different methods we actually used for the bispectrum, and but we actually used the direct method because of the fact that the direct method was less computationally expensive. In the training process, we had 900 images from each of the classes. We had seven classes, and we had 900 images from each of the classes that we used for the training. We also had 200 images for each of the classes for the validation, and we had 100 images for each of the classes for the testing of the model. So the diagnostic framework I mentioned, I showed earlier, actually has we have the input, which has the multiple fault signal. One of the parallel parts has the bispectrum, and the other part has the short-time Fourier transform. These were used on different CNN.
You have 1 minute left.
Okay. These were used on different CNN, and then ensemble was used to have the different conditions that were present. And in combining this, we use the averaging method to make the combination. So our results actually showed that most of the different fault combination were actually able to be diagnosed. We had that the training time for the spectrogram model was 2,702 seconds, while that of the bispectrum was reduced. So we had that the approach that we have actually gave a better test accuracy, which was 97.54% as compared to that of the spectrogram and the bispectrum methods. We actually went further to compare our method with the benchmark method, which has to do with envelope analysis when used for bearing and bearing fault. For we tried it on the inner race fault. We were able to get the characteristic frequency for the inner race fault, and then we had a combination of the inner race fault and the ball fault being present in the multiple fault signal. Or we found out that in that signal, we're not able to the ball spin frequency was actually missing, which could give misdetection in that particular case. Similar thing happened when we used the spectrogram alone for the comparison, and also when we use the bispectrum alone for the comparison. So in conclusion, we had an aim which was to detect multiple faults using to avoid failure, and by using our new approach, and that involved using the bispectrum and the spectrogram as inputs to parallel CNN for complementary features. That gave a flexible approach for the diagnosis of the multiple faults. Our result also indicated that there was a better performance, and misdetection prevented, and misclassification were prevented, which in our case could prevent a reoccurrence of the helicopter crash that occurred. Thank you for your time, and thank you for your attention. Any question?
Thanks very much, Adume. I was going to ask you about advantages, but I think you've answered that. What do you think about validation? What would you like to do next with this?
What I intend to do next is to use real multiple fault signal, and actually look at using the approach that I have, and to see how the method performs.
Okay, thank you very much. So we have, as far as I can tell, on the published schedule, an error because Adume was scheduled for 40 minutes. Our next session is Nithra Subramanian, who's going to talk about fault detection for aircraft fuel systems. And if I understand correctly, we also have an additional talk after that.
Yeah, you're right at the end.
So do hang on after Nithya has finished, because there will be another one after that. So Adume, if we could ask you to close your camera and to unshare your screen, please.
Right, okay.
Hello, I'm Nithya Subramanian. I have some issues with my internet, so I might be just doing the audio presentation instead of the video presentation, if that is okay. And I'll try to share my screen now.
Okay, carry on.
Thank you.
That's working fine, Nithya, and
Okay.
we can hear you, and we also see your screen.
Okay, thank you. So I'm Nitya Subramanian. I'm doing a PhD in fault detection in aircraft fuel system. I'm using various types of machine learning techniques for my PhD, but for this conference, I'm just using the neural network as a trial. So for the agenda of this meeting is going to be the background knowledge, methodology that I use, the process of data collection, data pre-processing, and the neural network that I have used, and the conclusion. So according to the study conducted by the International Air Transport Association in 2017, the commercial aircraft industry has spent more than 75 billion on maintenance, repair, and overhaul alone. And it is expected to increase up to 118 billions in 2027. In order to reduce this cost, most of the MROs use condition-based maintenance system, and also because the technological advances in the aircraft industry in the last decades has increased tremendously, which causes more complexity in maintaining the aircraft systems. This in turn makes the fault detection, diagnosis, modification, repair more difficult. The presence of faults within a system can result in a major accident, or in case of a minor faults, it can affect the performance of the aircraft systems and reduces the performance of the systems that is close to the components. In terms of maintenance, there are 3 types of maintenance that is used in general in various industries, that is preventive maintenance, condition-based maintenance, and corrective maintenance. The preventive maintenance leads to a costly maintenance strategy given the expense associated with the modern complex components. Besides, the preventive maintenance does not provide any information about the health status of the components, which is a major defect for safety critical of the components. This in turn increases the cost of the maintenance as the components gets replaced even if the components are healthy, just because of the time frame of the components has to be replaced. The corrective maintenance explains with the word. The strategy that is used in the corrective maintenance is the components that is failed gets replaced immediately. This strategy might work for the day-to-day use of the automobiles, the components getting replaced when there is an error or a fault, but it is not advised for a safety critical aircraft industry. In terms of, so this is one of the reason that the condition-based maintenance is preferred by the MROs, as it is more, the total cost of the maintenance is low, and the maintenance cost is low, and also the operating cost. And in terms of number of failures in the events and the safety criticalness, the condition-based maintenance is more preferred. The condition-based maintenance uses two methods, which is a diagnostics method and prognostics method. Diagnostics method is of 3 stages, which is fault detection, identification, and isolation. And for the condition-based maintenance, follows these steps of data acquiring, pre-processing, the feature extraction or selection, condition-based assessment or fault detection, decision making, and forwarding the decision made to the MROs for the maintenance system. So the data can be acquired by different methods, that is physics-based method, or it can be acquired using sensor data, sensor that is attached to the components. And in terms of pre-processing, the data acquired is pre-processed using cleansing, labeling, and visualization of the data. The feed is the feed or after pre-processing the data is sent to the prognostics or diagnostics algorithms. Then the decision made by the algorithm is sent to the MROs for repairing, replacing, or to continue using the component. The prognostics and diagnostics can be of two methods, which is physics-based method and mathematical-based method. So in terms of in terms of the data-driven method, it can use shallow learning or a deep learning method. Shallow learning, such as neural networks, which I have used for this paper, and the deep learning, which I'm going to use it for my further PhD research. So this is the equipments that I've used. That I've used for collecting my data. So this experimental setup is in the IVHM lab of Cranfield University. This is a replication of fuel system. So the fuel system for different the aircraft differs accordingly. So this setup replicates the fuel system of Boeing's 777. In this setup, the fuel system consists of is driven by motors externally, and it has internal relief valves, shut-off valve, one filter, and two tanks. One is taken as the receiving the tank that is full, so as a fuel tank, and the other tank is used as a sump, as replicating the engine of an aircraft. And so this experimental setup is used to replicate 5 different faults in the 5 different faults in an aircraft fuel system. So we have the shut-off valve. The sticking valve is used as we have a sticking valve. We have a leaking pipe, a clogged filter, clogged nozzle, and a block for flow meter. And after every fault, there is a pressure reading done. That's how the pressure difference is how the fault is being detected in this system. And for my data collection, I have used all these 5 different faults, and in different gradations as well. So I used it for 25% of a failure of one fault. For example, for a leaking pipe, I have taken 3 different gradients. So 25% leakage, 50% leakage, and 75% leakage. And for every fault, about 3,000 samples are being collected, which makes about 1.8 billion samples for faulty data and 2 million healthy data. And the data that is being obtained is cleansed and labeled accordingly. So the healthy data is labeled as 0, and the other faults are being labeled accordingly. And I used visualization method to check if my data is replicated accordingly. And after that, I'm using the neural network. So multi-layer forward neural network replicates the human brain. So it takes as the X is the input, and the first layer of neurons is taken, and after the process of the first layer of neurons, the second layer processes the input, the output of the first layer neuron, and the secondary data is the output of the final model. As a result, altogether, I got 13 signals and 2 targets. One is healthy data and one is faulty data. And I have used 70% of the data for training, 15% for testing, and 15% for validation. The model that I've used here was a scale conjugate gradient propagation method. The high level in this method, I have attained the high level of accuracy, but I have just used about 5,000 samples. For my further research for my PhD, I'm still going to use about 2 million time steps, uniform time steps of this data. I got a perfect result on the confusion matrix, 59% on the 59% and on the healthy data, and 40% on the faulty data. And the ROC also reflects a true positive rate. The sensitivity of the data is being predicted by using the ROC of RSC curve. So the neural network applied to solve this fault detection of the experimental data, and the fault diagnosis is more complicated problem for this neural network. For the further steps of my PhD, so I'm going to use it for recurrent neural network, and I'm going to use a fuzzy logic and SVM and compare the results, how it's formed. Thank you for listening.
Thank you, Nitya, and thank you for finishing on time, which I appreciate. Which gives us some time for some questions. So I'd like to ask you what you think the advantage of the neural network approach is, as opposed to a more kind of crystalline approach, addressing the faults in detail.
So the neural network approach doesn't use any human influence on it. So the data that is given is processed by the neural network on its own. So it reduces more faults, more induced faults.
And you presumably need quite large data sets to train the neural network. Can you comment a little more on the size of the data sets you need and the richness of the induced faults?
So the size of data, just for the healthy data, I have 2 million samples, and for each fault, so I have about 15 different faults. For each fault, I have about 300,000 samples of the data. So it's more like 1.8 million samples, which will be more, which can train the neural network.
And if you were going to discover a fault that was not trained, do you think your neural network is going to be able to discover outliers as well?
At this point, for this paper presentation, I have just done fault identification. I didn't do the classification. I think the neural network might just show there is a difference. So the neural network will just show it as a glitch. That's why I'm using different methods such as RNN and SVM to compare and see how it's going to detect. Each method is going to detect the faults.
Okay, I have also a question, Andrew, if
Yeah.
I may. Because there are always tension between starting from understanding the physical phenomena or taking into the let's say in consideration big data, and of course we cannot solve it right now. This debate, but my let's say my question is more which advantage do you see in using neural network with big data instead of starting from the physical phenomena?
So the physics-based method will involve physics-based method may give more accuracy than neural network. I should agree to that.
Usually it's like that.
But it's but it's more complex to understand, and for in terms of data-driven, data scientist or anyone who doesn't know anything about the physics of a component can process it and get a result. But in terms of physics-based method, we require the engineer who's specialized in the component. That's where the complex lies.
And it's a difficult let's say it's a difficult word and a difficult situation too.
We have a question on the Q&A page. Gustavo asks, are those actual fault data? So
yes, it is.
It's a real rig
fault
and
data.
it generated, well, real fault data or real simulated fault data? Because I think the fault was seeded.
Real simulated fault data, and yes, I have to accept that it won't be the same scenario when we are using. If I have to take the data from a real aircraft, because there'll be more disturbances, but this is more clean data.
A real rig, but with seeded faults on the rig. Yeah. Okay, thank you. We've got a couple of minutes left in case there are other questions. If not, we'll say thank you very much to Nithya. Virtual applause.
Thank you very much, Nithya.
Thank you.
And
thanks a lot.
Then we have a mystery presentation. So Alberto, do you have news about the presentation that's going on next?
Yeah, I have. We have a really final presentation about investigating the impact of human-in-the-loop digital twin in an industrial maintenance context. And I will, perfect. Ali, hello, welcome.
I hope.
So,
thank you.
We are really curious to look at your presentation.
Okay, thank you. I hope that today it will go on because I supposed to present yesterday, but I have a technical problem yesterday.
Okay.
Okay. So
no problem.
Hopefully it will work.
I
will just ask you to unshare your screen and to mute your microphone. And yes, Ali, we can see your the presentation. And do you have also the camera? Or you have?
I'm worried that it will. I will have the same technical problem like yesterday.
No problem. Okay, that's perfect. We can hear you. So the floor is yours. You have 15 minutes.
Okay. So my name is Ali Al Yaqub. I am a research associate at Loughborough University, and I'm glad to be here today to present my my work in this conference. So I'm working on a project Digitob with the on digital twin and digital technology. So today I will present my work on investigating the impact of a human-in-the-loop digital twin in industrial maintenance context. So the outlines of my presentation. So I will talk about the motivation, the proposed framework, and then I will give a brief introduction on Digitob, and then the conclusions and future work. So this paper, the paper I'm presenting, is a conceptual paper. We didn't do the experiment due to the COVID. So the motivation we've seen in many sectors that digital twin is impacting the performance and improving the data-driven approaches, such as in social media. And also in industry, we've seen some benefits of the digital twin. However, we missed one important element in this context, which is the human and the human expertise. A human in general, they have a superior perceptual capabilities, and they also have their cognitive capabilities. And they might indicate an abnormal situation in the shop floor in this industrial setup much faster than sensors. However, this very important source of data is missing. Also, in addition to that, in industrial or in manufacturing context, maintenance is very expensive. And it can cost from 14 to 40% of the production cost. So, given those facts, we believe that if we use more biological human data in the shop floor, we will be able to reduce this cost. We will be able to reduce the maintenance downtime and the overall cost. As one example, if we take the human-robot collaboration as an example, and if anyone of you is familiar with robot operating system, he knows that the equipment, the physical equipment, is well presented in ROS. So you can have a simulation which can replicate what's going on the shop floor. And here we are talking specifically about robots. You can get physical information about the temperature, the position of the joints, the force and torque, and the speed, acceleration, and so on and so forth. And this is very well represented on the virtual or the cloud or the digital twin of the physical equipment. On the other hand, and this is in human-robot collaboration, the other partner or the other active agent in that sense is the human. You don't have any representation of the human. You don't know what the human is doing. You might have some like contextual sensors to indicate where is the human relatively to the robot, but not much, not equivalent to the robot. So given that we have an EBS-RC project, which is Digitob, and in Digitob we try to focus on the human. So we try to provide the digital tools that can, on real time, give some indication and support to decision makers regarding how to use automation and how to use digital data in manufacturing. And the focus of this project is to use human factor theories, data analytics, and sensory technology. What we are proposing here is to use the human as a source of sensory data to try to reduce the maintenance downtime and cost. And to do that, we are proposing to use a 3-layer system, which basically composed of a physical layer. We have a robot, a robotized dispensing system, which is a six-axis ABB IRB 120 robot. We have physical sensors, which indicates the environmental, humidity, temperature. We have a set of cameras, and we have a GUI where the human can interact with the machine. On the second layer, we have the communication layer. And this is basically, we are using ROS, robot operating system. And on the third layer, we have the digital twin layer, where the robot or the equipment is well represented based on ROS. So we have we have a unity acid of the robot, which can replicate what's going on the shop floor. And also we have some data based models of the human to indicate his behavior. One of the things we have done is to predict when the muscle indicating a muscle fatigue on the human, where we can trigger that and indicate it. And we have a remote expert. The idea here to come up with a set of failures on the physical setup and try to ask the human to identify the root cause of this failure. And then we will try to measure, see what's the time, how long it takes to identify the root cause of those sets of failures. And then we will compare this scenario with a scenario where the human on the shop floor is supported by a remote expert with a VR. I've already explained this slide. Then so the whole idea is to measure those and give a more concrete results. But due to the COVID-19, we couldn't do any human validation of this. But our hypothesis still, we need to do validation in the future. But the idea, we believe that the providing such a framework will improve the maintenance, and it will add to the industry 4.0 using VR and include biological data about the human activity, and even his workload will reduce the maintenance cost. So the hardware setup is already done. We still need to validate our hypothesis. In the future, we need also to include more information about the human activities in the VR, which is still not done yet. So I try to be very brief. I know it's the lunch time, and if you have any questions, any suggestions, I'm happy to answer if I can.
Thank you very much, Ali.
Thank you. Yes, your timing is much appreciated. So how are you getting on with the ROV system? Is this something that you find is easy to use, or have you encountered some challenges?
Sorry again, I didn't. What system?
You're using ROS, Robot Operating System.
Yes,
And
yes.
How are you getting on with that?
So I'm using it for more than 6 years now, so I don't think. Some people will say it's a bit complicated, but now they are making it more friendly. You can use it with Windows 10. I start using it when it was Linux based, and a lot of people who are like, they don't feel comfortable working with Linux. You can use it with MATLAB right now, and Windows 10. So I think it's very convenient, and there are more tools, more people using it. It seems to be promising in the future.
Thank you. That's very helpful.
It seems really there is a growing community on that. You're right. I have also a question, Andrew, if I may.
Yeah.
And the question is, digital twin is becoming quite also a buzzword around, also
Yes.
also around the maintenance world, and a lot of industry, they are trying now to go for a digital twin solution, but most of the time they start also from a perspective that they don't know why they want to have a digital twin. They don't know how to use it, and that costs money most of the time. So, in your opinion, how your solution can solve these problems? Which suggestion you can give to the companies to, let's say, to have a more efficient?
So in the era where right now, I think you are right. Industries, they are a bit reluctant on investing more in adding more sensors. This is, I think, adding more sensors is coming, whether we like it or not. But the question is to collect the data and use it in ethical way. This is the challenge. The cost, in my opinion, I've worked with Siemens before on a similar project, and it seems that everyone would like to install more sensors. Everyone would like to use data-driven approaches. However, it's the question now, if we will include the human in the loop, what data will be okay to use, what data will not be a privacy issue, and so on and so forth. But I think the cost is not the main issue, in my opinion. Maybe I'm wrong.
Okay, I think that indeed is a debatable point, at least. Okay, thank you very much, Ali.
No worries.
Okay, shall we let folks get a bite to eat? There is a lunchtime workshop that I'd like to plug before we go off the line, which is our session on railway research. I hope to see you there at 1 o'clock. Arihit, you have a message for us.
Yeah, no, that's the thing I was going to say, that we're going to close this session and everyone will be sent back to their respective tables. I request everyone to go back to auditorium and join the workshop session, what Andrew said, from 1 o'clock. So I'm posting the link for that one under the general chat option, just to help you out, which will be easier for you to find. So that's there. So thank you, everyone. Thanks, Alberto and Andrew, for chairing the session. Thanks to all the speakers.
Thank you very much. Great pleasure.
Yep. I'm closing this session in 1 minute then. Thank you.
Thank you. Bye-bye.
Bye-bye.
Thank you.